I think we'll start our today's session. Very good evening to one and all. Right. So last class we started our discussion on cryptographic hash function, right? And we concluded with different applications of cryptographic hash functions. And in continuation with it, here are some of the techniques which have been used, like in which applications which uses cryptographic hash function, that is hashing along with the digital signature. This is one of the major application which will be satisfying all the three criteria, that is pre-image resistance, second pre-image, and collision resistance. And this collision resistance, it has a condition: if and only if your attacker chooses a attack called chosen message attack, then this hash plus digital signature can able to provide a resistance to it. Then we have another application called intrusion detection, virus detection. Like this best example is nothing but your firewall. I'm not speaking about anything antivirus. It's like a firewall, and like how we have Windows Defender kind of thing. Okay, it's like a one step below modern firewalls. So here also your cryptographic hash functions plays a major role. Especially this one satisfies a second pre-image resistance. We'll come to this hashing plus symmetric encryption in the upcoming slides. Okay. Then your one-way password file stack is going to satisfy only the pre-image resistance. Then message authentication code, which we'll be discussing after our cryptographic hash function in this module. Okay, this which is also going to satisfy all these three criteria. Right. So can anyone tell what is this one-way password file? People are using nowadays also. Any guess what is this one-way password file? Any example? Nowadays, everyone in the class have been using that one-way password file. If I give a clue, you can easily get me the answer. Whenever you are doing any online transactions.
Sir, OTP.
Yes, yes. All your OTPs have the base with hashing algorithm only. Right. Now we move into deep into how these cryptographic hash functions are going to be designed or going to be uh, developed. Okay. So already in the last class we said that the cryptographic hash function will take the messages of arbitrary length. Arbitrary length means any length. If there's no restrictions, the length can run up to infinity based upon the algorithm. So it's totally a variable length of message. Sorry. And it is going to create a message digest. Here is message digest is also called as simply digest, or it is also called as hash value, right, of fixed length. This is the main point. So whatever the variable length of message you're going to give as input to the hash function, it is going to give me output of a fixed length output, right? So this is the basic definition of cryptographic hash function. Right. So in this we'll be discussing what do you mean by iterated hash function. Okay. And what are two different groups we can able to classify based on compression function. So before moving into iterated hash function, okay, I think I'll directly explain it this one. This is the very basic structure for our hashing algorithm called Merkley-Damgard scheme. All the algorithms which have been designed or going to be developed with respect to hashing algorithm, I'm speaking, okay, will be based on this Merkley-Damgard scheme. Like how we had our symmetric key block ciphers. If you take our AES, DES, if you trace back the basic structure, everything will lead to a simple product cipher. Right. The same way for hashing algorithm, this Merkley-Damgard scheme is a base. So how this works on the sense, whatever the message you want to find the hash. Okay. So based on your scheme or based on your algorithm, you'll be padding them. Okay, not to make it as a multiples of something. So I hope everyone understand why we are going for padding. Okay, there'll be a padding bit will be added. Then this original message plus the padded message, everything will be taken as an input. So the next step is nothing but I'm going to divide them into multiple blocks of fixed length. In this case, I'm grouping them into n bits. n number of bits have been taken, and I'm dividing the entire thing into multiple blocks of n number of bits, starting from M1, M2 up to MT. Right. Then I'm going to supply with the value called H0, which will be made up of m number of bits. This H0 is nothing but the seed value. I hope everyone remembers this value, the name seed value, which we'll be using in our PN sequence generation. Same way, here also we are going to have initial value. It's called as initial value, and that is IV, or it is also called as a seed value. And this will be made up of m number of bits. Right. The only condition here in the sense your n will be always greater than m. It will be mentioned here also. Right. So n will be always kept greater than m. So accordingly, you will be dividing the block. So you will be giving the input to a particular function. Okay. M1 will be given as input and H0 will be given as a input. So some mathematical operation will be going inside this one, and will produce me an output called H1, which is nothing but the hash value. Okay. After first iteration. Okay. This function for the particular iteration is called compression function, and you can able to see this H1 is now given as a input for my second iteration. Okay. And M2 is given as input, and I'm again giving output as H2. So all this H1, H2, all these things will be made up of m number of bits. So this will be iterated. The iteration will be going on until I process the last block of MT, okay, with the function, same function f, so that I'll be getting the output called HT, okay, the final value, which is also m number of bits. That's why they're saying whatever the length of the message you're going to give, okay, I'll be getting a fixed length of message digest. Okay, so these things, individual mathematical algorithms are called compression function, and this entire process of entire thing is called as iterated hash function, or for ease of use, we used to call them as a simply hash function. Is it clear, guys? The difference between compression function and hash function? If it is clear, raise your hand. If you have doubts, you can ask me. And I hope you also understood the concept how whatever the length of your original message you're going to feed, it is going to give me output of fixed length. Right. Thank you, Arun. What about others? I hope it is clear. Right. So now we move on to the two groups of compression function, because here the heart of the entire hash function is nothing but this compression function only. This iterated hash function is nothing but how much time I'm going to repeat it. That's not going to make much difference. So the entire thing lies on this compression function. So based on the compression function, how it is designed, they are grouped under two categories. Right. One is called any compression function which is made from the scratch, which means that the mathematical algorithm is in particular it is made one and only for this compression function. Okay. The other category is nothing but we are going to make use of symmetric key block ciphers, to be specific, like your DES or AES kind of algorithms. Okay, where you're going to use symmetric key block ciphers, which will act as a compression function, like how we are using our symmetric key block ciphers for PN sequence generation. Similar way, we can also make use of these encryption algorithms also to perform the compression function. So under this crash function, we have two variants, which most important algorithms which are still in use, called MT, which stands for message digest, then SHA, which stands for secure hash algorithm. And under our symmetric key block cipher, we are having a function, compression function called whirlpool. So we'll be discussing all these three algorithms in this module. Okay. So if you see the comparisons of the scratch functions, we have MT5, which is the latest message digest, which is still in use. SHA's first variant is SHA1, and I have RIP EMD. Okay. This is also another algorithm, but we won't be discussing this one since it is not in our syllabus. Right. So here you can able to see the digest length, or simply your hash value for MD5 is 128 bit, SHA1 is 160 and 160 bits. And the basic unit of processing. The basic unit of processing is nothing but this one. This M1, the size of this M1s or 512 bits in MD5. Okay, here also 512 and 512. And number of steps, how we used to call them in rounds in our AES, here we'll be using a term called steps. Okay, so here totally 64 steps, that is totally 4 rounds, each round having 16 steps, so totally 64 steps. Here again 4 rounds for 20 steps, so it will be giving me 80 steps here. And here the same thing, but here the 5 paired rounds of 60. That means you'll be getting 80 plus 80, which are going to be going on in a parallel way. So they say it as a 160 steps. Actually speaking, at a time 80 steps will be running, but parallelly they are running, so 160 steps. And here the maximum supported message size. Okay, MD5 just pushed for infinite length. Whereas SHA1 we have a limitation up to 2 power 64 minus 1. Same for this one. And primitive logic functions. These logical functions are nothing but our similar to our Boolean functions. How we have XOR operation. There is also other operation called if and majority operation. We will be seeing them in the upcoming slides. So totally MD5 uses 4 different types of logical functions. SHA also 4, and this one goes 5 different types of logical things. Then additive constants, like how we have addition of constant values. If you remember properly, the key expansion of our AES, round constant we used to call. Like this, we have constants here also. So MD5 have 64 constants, and SHA have 4, and RIP have 9. And NDNS, we'll see what this NDNS means while discussing the algorithms. Right. Then if you see the characteristics of secure hash algorithms, we just saw the now SHA1. So it has been evolving from SHA1 to 224. Now presently we are using SHA512, and we'll be discussing this one for our detailed discussion. Right. So here the maximum size I have pushed to 2 power 128 minus 1. And here they increase the block size also 512, as well as the hash value we have been pushed to 512 bits. Right, and number of rounds is 80, and word size. So each word, I mean, totally made up of 64 bits. Total size of words in terms of bits, if we say. Right. I hope you remember words, bits to byte, byte to words, everything. The same thing here is utilized here. Now we move on to hash functions based on block ciphers. So till now we just saw some of the hash functions which are based on scratch functions. That is this MD comparison of scratch functions. This one is nothing but a hash function based on block ciphers. Right. So they'll be using some encryption algorithm. There are different schemes proposed. Okay, some of the prominent schemes I'll be just showing here. Okay, one is called Rabin scheme, the first one. So they'll be having the parent message. So whenever I say a parent message means after adding the padding bits. Okay. And they are dividing them into t number of blocks, n made up of n number of bits, and similarly I'll be having a m bit of seed value. And here the seed value will be given as a plain text, and here I can use any symmetric block cipher. Right. So here we have a plain text, and the key, in place of key I'll be placing the M1 block, and the cipher text produced is nothing but my H1 value, that is first hash value, which will be again given as input for my plain text in the second iteration, and this will be computed until I complete my last block, and the final output of the cipher text will be taken as my message digest here. This is a basic Rabin scheme. Then I have Davis-Meyer scheme. In Davis-Meyer scheme, they were, yes, yes.
Sir, for the previous one, can we use any like different symmetric block cipher techniques for each block?
No,
or
no.
we have to use the same throughout?
You have to use the same. You have to use the same. For example, if you're using AES here means you have to use the same AES for all the iterations. You can't change one block with another algorithm.
Okay.
That I'm speaking with respect to Rabin scheme. Suppose if you are going to design on your own, it's most welcome. Why they want to go with the different thing in the sense, For example, here, if you're going with, assume that you're going with the DES algorithm, the output will be coming out as 64 bits. Okay, and you are choosing here, you're going with AES. I need an input of 128 bit. So I have to convert the 64 bit into 128 bit, and the output will be getting as 128 bit. Suppose for next compression function, again you're going with DES. Again, you have to compress them to 64 bit. But you can design on your own. As per Rabin scheme, they'll be using same one. If you want, you can also design these things. If you are inventing any process for expanding and compression without loss of data, then you can perform it. And here, loss of data also nothing, because you are not going to what can you do? Do the reverse process of hashing algorithm. Yeah, the point which you are said is correct. You can also perform that one also. You can just do it. Anyone have done such things or not? If not, you can do. It's not it is not like you shouldn't do. In Rabin scheme, they didn't mention this way.
Okay, sir.
Then comes Davis-Mayer scheme, and here also you'll be using the same block cipher only for all the thing. The only difference here is that they took a feedback. That is a plain text which has been given as an input. Here will be taken here, and the value coming out of cipher text will be XORed here. And the output here is nothing but my hash value. So this is repeated for all the T blocks, and the final output is taken as a message digest value here. Okay, next one comes Matthias-Mayer scheme. So in this one, can you people able to spot the difference between Davis-Mayer and Matthias-Mayer? Here, that what they did in the sense, they simply changed the input. That is, here the seed value is given in place of key, and the parent bits are given in the place of plain text. If you see in Davis-Mayer scheme, here the parent bits will be given in place of key, and the seed value will be given in the place of plain text here. Right. So that's the only difference here. They simply swap the positions of plain text and the key. You can able to see here. And the other signal flow is same, and it is repeated for the last block, and the final output will be taken as a digest value. And the most sophisticated one is Miyaguchi Prinell scheme. And here, what it is, they try to XOR all the inputs with the output. They took the seed value, they took the plain text input, that is a parent bit, and the final output of ciphertext is going to be XOR with all these three to get me the hash value here. And this is repeated for T blocks, and the final output will be again XOR. So here XOR means you can able to see all these three values will be of same size or same length, so that I'll be getting the same output of message digest here. Right. Is it clear, guys, regarding the schemes? All these four? If it is clear, raise a hand. Oh, thank you, Kashish. What about others? Okay. Now we move into MD4 hashing algorithm. How this MD4 is going to work. So again, MD4 is also a message digest algorithm designed by a professor in MIT. If you remember properly, all the inventions of cryptographic algorithm came from MIT only. Right. So here this is also found in 1990 by Professor Ronald Rivest. Okay. So actually he started this one. Actually, if you see the tree, he started MD4. From this MD4 only, this RIP EMD came, SHA came, everything. So that he is the founder of all these three existing hashing functions. Okay. So he had initially he started with a digest length of 128 bits. And this one only influenced, as I said, the present day MD5, SHA algorithms as well as RIP EMD. Okay. And MD4 is used to compute the password digest for our famous Windows, NT, XP, Vista. Nowadays, people are not using this OS. Yeah, these things they used MD4. Okay, 1992, the weakness of MD4 has been found. Okay, so again, the professor reversed. Okay, he has to strengthen this algorithm. Okay, but in order to strengthen the algorithm, he increased the complexity. Thereby, he made a slower version called MD5. Okay, because the weakness has been found and it has been proved in the year 1998 by a person called Robert. Okay, he found the first MD4 collision. He made the collision in MD4. That is, he disproved the third property of collision resistance. Okay. So he created a collision and he showed in 1998 that way the MD5 came into existence now. Right. So this is how came in 90s. Reversed investor, found MD4. Then SHA found by NIST. It's a group of people 93, 95, and SHA 512 was found in the year 2002 and ratified in 2004. And RIPMD has been stopped in 96, and MD5 okay, which is ratified in 92 and still it is used. Okay. Oh, 1 second, I'm just 625 minutes, fine. So if you see MD4 family, okay, it is totally based on our Mugelan design principle. If you remember properly, just now we just saw the iterated hash function. So here you'll be having the message blocks, okay, and you will be creating multiple blocks of this messages, and each block will be divided into multiple words, and this one will go for multiple. Now there is nothing. IV is nothing but an initial value, or also called a seed value, which will be given as input for a. This is one of your compression function. This will be repeated until finish the entire message block, and the final output which are going to come out is going to be XORed here with the seed value here, and the output is taken. So this one word W0, W1, W2 is nothing but different blocks of the message length. This is the basic construction of our MD4 algorithm. So hope this process is clear, right? So that I'll move on to the data structures. If it is clear, kindly raise your hand. Okay. Because the next step which I'm going to say is may confuse. So I want everyone to listen to it carefully. If you have any doubt or if you're getting confused anywhere, kindly stop me there and ask me. Right? Okay, now we'll see how the input messages are going to be formulated. Like, so we'll be taking a 512-bit input message. Now I am speaking after creating the block. That is, if this one Merkley diagram. Okay. After I am taking this one block, now I am speaking about this entire 512 block now. I'm not speaking about how this 512 block have been came. So after obtaining this 512 blocks, how the input message is going to be modified here. Okay. So this one 512-bit input message block will have 16 words. This point you people have to remember. 16 words starting from M0 to M15, right? And each message word will be made up of 32-bit. Is it correct? One word. Can anyone tell one word made up of how many bytes? Simple question. How many bytes make one word? Guys, if you remember properly.
So 4.
Yes. 4 bytes. Once again. 4 bytes. Right. So if you convert this 4 bytes into bits, I'll be getting 32 bits. Right. So because each byte is made up of 8 bits. So 8 into 4, I'll be getting 32. So each message word is made up of 32 bits, and this bits, each and every bit will be denoted as M, K, comma, J. So J will range from 0 to 31. How, for example, if I say M01 means, what I mean in sense, I mean in the word M0, I am speaking about first bit. If I say M, can say like 95. Okay, this M9 means M95 means I'm choosing the word M9. In that, I'm taking the fifth bit. So each and every
Excuse me, sir.
yes.
Sir, it's varying from 0 to 31, so it should be second bit and sixth bit, right?
Oh, sorry. Yes. If I say this one M01 means if 00 means first bit, 01 means second bit. Yeah, correct. Sorry. And here 9 means 95 means this
Sixth
is
bit.
sixth bit. Thank you, guys.
Oh,
So like this, you can go for like M10 comma 30 means 31st bit. Okay. So I hope this is clear now, right? This is all about the input message you people have to know. Then comes the register words. This is a technical term used only in our MD4, which is nothing but the name given for our seed value. The seed value is also called as register words. So how many bits make that register words? 32 bit makes register words, which means I'm going to have register word made up of, I mean, one second. So 32-bit register words means how many words are present there? Can anyone tell?
one word.
Okay, one word. Okay, so it's called as a one word, and this one word is going to be going through different modifications of totally 48 steps it will undergo actually. That's why it will be denoted as AI based upon which step that word is sitting. Okay, this I value will be ranging from 0 to 47. We will see how this one happening while discussing the flow of our register words. And before moving into this one, I want to convey one thing. Don't worry, you won't get any numericals based on this hashing algorithm in our cat or fat. It's only conceptual thing because it's very difficult to ask you on the numerical in MD4. Very basic things, maximum of worthy of 3 or 5 marks. We'll see where it will come. We won't ask you to the entire flow of hashing and all. Right. So as of now, just listen to the flow because most people will think in sense by seeing this, sir, how can we able to manipulate these things in examinations? Don't keep those things in mind now. So 32-bit register word, and this word, each word will be going under 48 steps. We'll see how this one, and the register bits. Okay, so this register bits will be represented as A, I, comma J because bits will be ranging from 0 to 31, and this each and every bit in every step will be represented as A, I, comma J, which means that if I say A 11, comma 14 means the word is going in the 12th step, and I am speaking about the 15th bit in that thing. So I comma j, like how we have k comma j, j always represent the bit. Here I represent the step here, and here k represent the word here in this input message. Now 4 output registers will be taken as an output of each and every step. After completion of each step, I'll be grouping 4 words and how, sorry, 4 register words. How in the sense, for example, if I is assume like, can I say, okay, for understanding, I'm going with fifth step. Okay, I is 5. So I minus 3, that is A2, comma, A5, comma, A4, comma, A3. I'll take these things, sorry, and this will be output of my one iteration, just not first iteration, of one step or one iteration. Okay. So this is how register words will be keep on changing, right? And what are the Boolean functions which are going to use? I mean, as I said, the logical functions which we just saw in the table. There we saw for MD5 we have 5 functions, 4 functions. For MD4, okay, for each and every step, okay, I will be using one type of Boolean function. Out of this 3, we'll be using only one. So X, Y, Z are nothing but 32-bit words. Each X is made up of 32-bit. This is 32-bit and this is 32-bit. Or simply speaking, they are nothing but word 1, word 2, word 3. And these three words will undergo some Boolean operation based on the step number. So one operation is if, majority operation, and XOR operation. So I hope everyone knows how XOR operation works. And this is the majority operation with respect to they return with respect to our XOR function, and this is a if operation which they are represented with respect to XOR function. Don't worry, I will teach you a simpler way to easily remember this majority and if function while solving the example. So as of now, we are just seeing what are the building blocks of a MD4 functions, how the input message will look like, how register words will be undergoing the changes, and what are the Boolean functions present here. Now, how the message is going to be prepared? Incoming message has to be in multiples of 512 bit. That is our concern, because each and every block will be made up of 512 bits. Right. So here the padding will be done by adding bit number 1, then followed with how many number of zeros you whatever you want to complete the entire length. Okay, so how this one is going to be done is not simply by adding the pads. I am going to get the 512 bits, because if you take MD4 algorithm, I want everyone to listen to this very carefully. You'll be having the original message here. Okay. Then I'll be using a 64-bit, last 64-bit. Okay, will be used to convey what is the original length of the message. The original length. Assume that it is made up of 400 bits. Okay. So this 64-bit will carry the message that the original length is 400 bits. So now 400 is the original message plus 64 is the message, I mean a bit used for conveying the original message. Okay. Now the remaining rest, assume this is the expanding message, will be added now to make it as a 512-bit block. Can anyone tell what are the remaining bits required here? Totally 464 plus x should give me 502. What is the value of x?
48.
That 48 is nothing but the padding bits. So the 48 bits, how it will be written in the sense, I'll be writing 1 followed with 47 number of zeros. Right. So here this altogether should come to a multiples of 512. Is it clear, guys, how this padding concept works? Not simply by if 400 means I'll be adding 112 not to make it 512. No, 64 will be used to convey the original length message. Then only the remaining thing will be done with the padding, and the padding will be sitting in between this original message and the last 64 bits. Then only the receiver can able to track the last 64 bit he will be taking, and he will saying that what is the original length message. So he will come to know from where the padding bit starts and where it ends easily by knowing the original length. Is it clear, guys? If it is clear, can you raise your hand?
Excuse me, sir.
Yes, Kashish.
So padding, like will we say that 48 bits is padding or 112 bits is padding?
Okay, this 48 is alone is called padding. This is nothing but the bit which is used to convey the message length. Actually, here they said this entire thing is called padding. Okay, in the diagram, once again. In this diagram, they mentioned this entire thing is as padding, but actually speaking, this is alone padding, because if I mean padding means I should have here also 1 followed with a 0 alone. Okay, actually speaking, this is alone padding. This last 64-bit is used to convey my original length of the message, because padding alone will be having 1 followed with rest of zeros. Whereas a 64-bit will be, for example, if I convert this 400 bit length as a 64-bit value means I'll be placing it here in the entire 64-bit. Is it clear?
Yes, sir.
Anyone have any doubts on this one? right? I hope it is clear, right? As I said, this 512 bit block of pattern message is going to be compressed because I am going to compress it to a fixed length at last, right? This 500 bit compression is going to happen in 3 rounds, and each round is going to be made of 16 steps. That's why 3 into 16, I'm going to have 48 steps. This is the part I just said, how this each and every word is going to be manipulated here. From 0 to 47. Right. And as I said, for each round, a different Boolean function will be used. That is, if I say I is now denotes the step. So here 0 to 15 is nothing, first 16 steps. If I put a round number here, this is round 1, round 2, round 3. For first 16 steps, the Boolean function is nothing but this one, and the round constant used for this first 16 steps of first round is this one. And if we're going for second round, okay, that is from 16 to 31, next 30, for next 16 steps, the Boolean function is majority function, and this is the round constant used. And for the next round or the last 16 steps, the XOR operation will be used as a Boolean operation, and this is the round constant used in last 16 steps. Is it clear, guys? This part, the how this Boolean function is going to be used in different rounds and different constants for these rounds, right? I think with this I will wrap up today's session, because here comes the most important thing. This is nothing but our hashing algorithm. How this entire operation, whatever we just saw now, okay, this one shows the entire manipulation on this one. So I want to discuss this in the next class. Okay, so because I don't want to rush up this part. Right. So with this, I'll wrap up today's session. So if anyone have any doubt in today's session, you can ask me now. If it is clear, kindly raise your hand.